Hello everyone. So today we will be talking a bit about mechanical properties of polymers. So in this lecture we will first talk about the some of the basics or basic definitions related to some mechanical properties. So we will start off with the definition of what's stress, what are the different components of stress that can be identified, and similarly we will also talk about the concept of strain. So stress and strain are some things that might be familiar to many of you, but we will talk about it in a more general sense and see that for any given material there are many different components of stress and strain that are possible. And then we will talk about the relationship between stress and strain. So how stress and strain are related, what kind of different mechanical properties like the different moduli which can be identified based on the relationship between different types of stress and strain. Then towards the end of this lecture we will focus on the elastic deformation of polymeric materials. So stress strain behavior of polymer materials of different kinds, that is what we will focus on towards the end of this lecture. Stress, as many of you might know, is generally defined as a force acting on a unit area. So force per unit area that is acting on a surface. Okay. So it is acting across a surface. So if we talk about let us say solid material and we take a section across this solid material and we focus on one of the surfaces, then the stress basically can be identified as the force per unit area being exerted by part of this solid material or the collection of molecules within the solid material on a different part of or adjacent part of the solid material. Similarly, for fluids also such internal stress can be identified. It will have units of force per unit area which in SI units is Pascal or Newton per meter square. So if we have force acting per unit area on a given surface as a definition of stress, then depending on the orientation of the surface relative to the direction of force that is acting, several different components of stress can be identified. So if we talk about the stress at a given point in a given coordinate axis, so if we let us say have a axis system defined by these three axes where we will call them x1, x2 and x3, one can equivalently call them as x, y, z also. So that does not change anything about the fundamental definitions. If we consider any point in this coordinate system, then the stress around that point can be defined by first let us say constructing a small kind of cubic element around this point, and then identifying the different stress components that are acting on the different faces of this cube. So if we talk about this face, the face which is perpendicular to x1, okay. So if we have some force acting on this face in some arbitrary direction, we can resolve that force into three different components, that is the components along the x1, x2 and x3 directions, and then we can calculate the appropriate stress component by dividing the force components that we have identified by the corresponding area of the face on which the force is acting. So on this front face which is perpendicular to this x1 axis, if we have some force F acting due to let us say the presence of surrounding material, then this force can be broken down into the three components Fx1, Fx2 and Fx3 let us say, which are the components along the three coordinate axes that we have drawn here. So Fx1 will be the force component parallel to the x1 axis. Now the surface that we are talking about is perpendicular to the x1 axis. So this force component Fx1 will also be perpendicular to the surface that we are talking about. So this Fx1 force is the normal force on this surface whereas the other two forces Fx2 and Fx3, these will be parallel to the x2 and x3 axis, and again the surface that we are talking about, this surface is also parallel to x2 and x3 axis. So the forces Fx2 and Fx3 are actually parallel to the surface on which they are acting. So these forces are referred to as shear forces. So and the corresponding stresses due to these forces will be the shear stresses. So once we have broken down the forces into the different components, then the force per unit area for each of these force components will give the corresponding stress components. So the 9 stress components that we have written down here, these 9 stress components correspond to basically the normal as well as the shear stress components that will be acting on let us say surfaces that are perpendicular to x1, surface perpendicular to x2, this one, as well as this top one surface perpendicular to x3. So if we identify all the stresses acting on these surfaces, we will end up with 9 such distinct components. Okay. A typical stress description of stress in a given material involves 9 different stress components. So stress is normally called as a tensor quantity, and this stress tensor, which we have denoted as this bold sigma here, this stress tensor can just be represented as a matrix of all the 9 stress components that we have identified. If we talk about, let us say, the stress component sigma 1 that will correspond to the force acting normal to the surface that is perpendicular to x1. So if we have this surface perpendicular to x1 here, then the force, normal force acting on this surface, that will be Fx1. So Fx1 divided by the surface's area, that will correspond to sigma 1. Sigma 1 2 will correspondingly be a stress component on that same surface, but due to the force Fx2 which is parallel to the surface area. So sigma 1 2 will be a shear stress component. Similarly, sigma 1 3 2 1 2 3 3 1 3 2, these will be shear stress components, and 1 1 2 2 and 3 3, these will be the normal stress components, because here the force is acting normal to the surface. Okay. So normal stresses, as we have identified, are sigma 1 1, sigma 2 2, sigma 3 3, and these are the diagonal elements in this stress tensor, and the off diagonal elements constitute what we call the shear stresses. So if we are pressing against the surface in this way, then the corresponding stress being generated is the shear stress. So it is acting parallel to the surface, and normal stress due to force acting perpendicular to the surface. We have 6 such shear stress components and 3 normal stress components. One thing to note again is that the shear stress, all these 6 components are actually not independent of each other. It turns out that the stress tensor is symmetric. What that means is that sigma ij equal to sigma ji, or in other words, for this the stress tensor that we have written here, the sigma 1 2 will be equal to sigma 2 1, sigma 2 3 will be equal to sigma 3 2, and same for sigma 1 3 and 3 1. So this is a condition that results if one applies the condition of rotational equilibrium on a given element, and then that equilibrium condition leads to the fact that the the stress tensor is symmetric, and the shear stresses are not independent of each other. Only 3 shear stress components are independent. The shear stresses are related in this way to each other. Another important thing to note about these normal stress is that typically when we talk about pressure, let us say inside a fluid, so hydrostatic pressure inside a static fluid, so that is also related to the normal stresses, and the relation between the normal stresses and the hydrostatic pressure, which is P, is just 1 by 3 times sigma 1 1 plus sigma 2 2 plus sigma 3 3. So hydrostatic pressure can be thought of as just the average of the normal stresses at any point inside a fluid. And as we have already mentioned, the stress tensor has only 6 independent components because shear stress components are related to each other. So this is some fundamental material about the quantity stress. Another important quantity that invariably comes up when we talk about mechanical properties is what's called the strain. So strain is again something that you would have come across earlier also. So it can be thought of as a deformation resulting from the relative movement of particles or atoms and molecules constituting a given solid due to the action of certain let us say external element like external force or anything like that. And strain is typically defined as the change in any dimension produced divided by the original dimension. So if we are talking just about a simple uniaxial tensile force acting on something, so if we let us say have this rod, and if it is being pulled down along a fixed axis, let us say along the axis of this rod in a using a tensile kind of force, so it is being pulled down. So the corresponding strain produced will simply be the ratio of the change in length divided by the original length of this rod. So for simple cases, if we let us say have, as we discussed, have a rod of original length L and it is extended to a length L prime due to the action of some external let us say tensile force, then the strain is simply defined as the change in length divided by the original length. But in general, so the strain can be thought of as a change in dimension divided by any original dimension due to the action of some external applied stress. So this is a simple definition of strain, and it is fine if you have a very simple kind of system where only a elongational kind of tensile force is acting and the deformation of the body is only along one direction. But in general, one can think of as a combination of stresses normally acting on a given body, where the we can have either tensile or compressive stresses acting simultaneously in different directions, along with shear stresses also acting on the material. So if we have such a general kind of case where many different kind of stresses are acting together on a given body, then the corresponding strain produced will also cannot also be defined by a single quantity, but instead it will also have many different components. So in general, a deformation can involve various different types of stresses and thereby various different directional deformations. So we can have shear deformation, extension, compression in various directions. Due to this, proper description of strain in a material can be given by identifying again 9 different components of strain, and that is done through this strain tensor. So strain tensor is also a tensor quantity, and both stress and strain tensor are referred to as what is called a second order tensor. Both of them have 9 elements. So again, if we talk about the diagonal elements epsilon 1, 1, 2, 2 and 3, 3, these correspond to the normal strain. So due to the normal forces or normal stresses acting, whereas the combination of stresses where shear stresses also might be present, that can also produce angular deformation along with linear deformation. So these angular deformation are characterized by these kind of shear strains that we have here. So again, we have 3 normal or tensile strains corresponding to the deformation in the 3 axes that we have defined, and we can also have shear strains which will be due to the action of usually shear stresses, and these will correspond to some kind of angular deformation of a body. So if again we have this rod, if it is pulled down, that will induce a normal strain in this material. On the other hand, if we have some body like this, and if we shear it by applying a shear stress on this surface, and the body which initially is this, it deforms, changes its shape. So that change in shape will correspond to some kind of an angular deformation, and that is quantified by these shear strains here. So again, like shear stress, the shear strains are also not independent, they are also related to each other, and the strain tensor is also symmetric. So sigma 2,1 and sigma 1,2 are equal, similarly sigma 3,1 and 1,3 are equal, and 3,2 and 2,3 are equal. So strain tensor is symmetric just as the stress tensor is symmetric, and we have these 3 conditions. So again, only 3 shear strain components are independent, and overall we have only 6 independent strain components. So the strain tensor only has 6 independent components. So now that we have some idea about the stress and strain and the different components that are necessary to describe stress at a point or strain at a point inside a body, now we can move ahead now and talk about the relationship between the stress and strain. Okay, so if there's a certain kind of external force applied resulting in certain stress in the material, what kind of strain correspondingly will be produced and so on. So a very simple kind of relationship between stress and strain is something that most of you would have come across even in high school physics, and that's what's referred to as the Hooke's law. So Hooke's law is a linear relationship between the stress and strain. Okay. So on the application of a certain force on a given body which produces a certain amount of stress, a proportional amount of strain is produced. That's what this Hooke's law predicts for elastic materials. And what's observed is that for many materials is this kind of a law, this linear relationship or a direct proportionality between stress and strain is found to be valid, provided that the amount of strain produced is small. So for small strains, this kind of Hooke's law is obeyed by many different materials, including many different polymers as well. However, if the strains are large, then deviation from Hooke's law and deviation from this elastic kind of behavior is commonly observed. For low strains, we can say that for many polymers, this kind of Hooke's law behavior or a linear relationship between stress and strain will be observed. So if we again talk about very simple kind of deformation, where we have a uniaxial tension or compression. So uniaxial means in one direction, and again if we consider this rod, then tensile force will be would be something that pulls this rod, whereas the compressive force will be something that pushes on this rod. But this extension or compression that we are talking about is only uniaxial, so only in one direction. So if we have such a case, then the Young's modulus can be defined as the proportionality constant between stress and strain. So if Hooke's law is valid, and if we are talking about a uniaxial kind of deformation, either extension or compression, then the stress is equal to the Young's modulus times the strain, or in other words, the Young's modulus is defined as the ratio of stress by strain, stress and strain. Of course, within the limits of the validity of Hooke's law, this Young's modulus will have a constant value. So now we have talked about again a very simple case where we have only discussed a uniaxial kind of deformation. In general, again we can have a deformation which can have many different components. So we can have deformation in different directions, including both normal stresses as well as shear stresses. Okay, so we can have a shear stress action that can change the shape, as well as we can have normal stresses that can change the linear dimension. So all these together, when considered in combination, for such a general case, this simple kind of example that we have shown here will not work, and a more generalized version of Hooke's law is needed. In general, the relationship between stress and strain components in tensor notation is written like this. So this stress tensor is related to the strain tensor through another quantity C, which itself is a tensor, and this C is actually a fourth order tensor, and it contains all the stiffness constants that relate the stress components to the strain components. So such a kind of description is commonly referred to a generalized Hooke's law, because now we have considered all the kinds of deformation and the corresponding relation between all the stress components and strain components. So here what's assumed is that all the stress components actually are functions, linear functions of all the strain components that are present. So if we talk about sigma 1 one can say that it will be related to strain component epsilon 1 by some quantity A11, which will be a corresponding stiffness constant, and but it won't just be related to this single strain component, but it will also be related to other strain components. So A12 epsilon 12 plus A13 epsilon 13, and so on and so forth, all the way up to let's say A32 epsilon 32 plus A33 epsilon 33. Okay. So we will see that there are actually for the description of this single stress component in terms of all the strain components, there correspondingly 1, 2, 3 and if we count all the terms, there will be actually 9 such constants. So there will be 9 constants. These 9 constants are the 9 what we call stiffness constants or elastic constants. And similarly for sigma 1, 2 as well, similarly the relationship with all the different strain components will be there, including other stiffness constants. So for sigma 1, 1 we have 9 such constants appearing. First the expression for sigma 1, 2 also 9 different constants can appear, and for sigma 1, 3 again 9 different constants can appear, because we are assuming that all the stress components are linear functions of all the strain components present. So similarly, if we go on in this, we will see that actually 9 times 9, that is 81 different stiffness constants or elastic constants are possible in this generalized Hooke's law kind of description of stress and strain relationship. So 81 stiffness constants are possible, but it turns out that we have seen that sigma and epsilon are actually symmetric tensors. So the symmetry conditions actually reduce the number of stiffness constants that are independent to only 36, and then some further considerations are there which actually reduce the number of these stiffness constants to 21 independent constants. Okay. So ultimately, if we take into account the fact that the stress and strain tensors are symmetric and some other considerations, then it turns out that only 21 of the original 81 stiffness constants are independent. So these 21 independent constants are the relevant one. Now depending on the specific crystalline material that we are talking about, the crystal structure that it has, the symmetry of the crystal structure actually can further reduce the number of independent elastic or stiffness constants. So crystal symmetry can further reduce the number of stiffness constants, and for example, if we are talking about a cubic crystal system, then the symmetry of this cubic crystal system results in the fact that only 3 independent stiffness constants or elastic constants are present. All the others are basically dependent on these 3 independent constants. So for a cubic crystal system, only 3 independent elastic constants are there. For another kind of crystal system which is not as symmetric, that is the orthorhombic crystal system, there 9 independent elastic constants are there, and these 9 independent elastic or stiffness constants are required to describe the elastic behavior of such orthorhombic crystals. So again, depending on what kind of crystal system we have and how much symmetry it has, the number of elastic constants actually goes further down. Another special case is if we have a material which is isotropic elastically. So when we say isotropic elastically, what we mean is that in terms of the elastic properties, the material is isotropic, that is the elastic properties of the material are direction independent. The different elastic properties of the material do not depend on the direction in which the property is being measured. So if we have such isotropic elastic solids, then in that case only 2 independent stiffness constants or elastic constants actually exist. All the others are dependent on these 2. So when we say isotropic, it's a material which whose properties do not depend on the direction in which the property is being measured. So some examples of polymer systems which can be considered kind of elastically isotropic is glassy polymers as well as semi-crystalline polymers. So semi-crystalline polymers also to some extent can be considered as isotropic, because of course the amorphous matrix in that material will be a kind of isotropic material, and we can think of the crystalline domains as just randomly and regularly distributed in this amorphous matrix in the semi-crystalline polymer, and overall we can think of this material as being kind of elastically isotropic as well. So glassy polymers or semi-crystalline polymers can be thought of as isotropic elastic materials. And when we say glassy, it's important to note that glassy is still a completely amorphous material, it does not have any order or crystallinity. Now if we focus specifically on elastically isotropic solids, okay. So let's first define a few quantities which characterize the mechanical properties of materials, and then we will try to relate or will discuss the relationship between these quantities that is valid for elastically isotropic solids. So, the first quantity that we will define is what is called the shear modulus of a material, and the shear modulus is defined as the linear kind of proportionality constant between the shear stress acting and the corresponding what is called shear strain that is produced. So, specifically the ratio is between shear stress and what is called the angle of shear. So, as we discussed, this shear kind of deformations are actually angular deformations. So, if you have a surface, if it is being sheared, it will be angularly deformed in a way. So, this kind of angular deformation can also be quantified by what is called the angle of shear and represented by the symbol gamma here, and this angle of shear is nothing but 2 times the corresponding shear strain. Okay. So, for a shear stress in the material represented by sigma 2,3. So, sigma 2,3 will be a shear stress where the force is parallel to the let us say axis x3 that we have discussed earlier, and the surface itself is also parallel to this this axis x3, but the surface is perpendicular to axis x2. So, the corresponding shear stress due to this kind of a force and surface arrangement, that is the sigma 2,3, and corresponding shear strain is epsilon 2,3, and the angle of shear, which will be just twice of this shear strain, that is gamma 2,3. So, this ratio is how the shear modulus is defined, and of course, one can have other kind of shear stresses also. So, this is only one component of shear stress. We have actually 3 independent shear stresses. So, their corresponding ratios, the corresponding shear stress and the corresponding angle of shear, they will also constitute this shear modulus. And since we have elastically isotropic material, all these shear moduli measured using different components of the shear stresses, they should come out to be equal because the material is isotropic. So, in general, this shear modulus is shear stress by angle of shear, where angle of shear is directly related to the shear strain by a factor of 2. In many cases, this instead of angle of shear, the shear strain itself is considered in this definition, and there in such cases the shear strain that is defined is equivalent to the angle of shear that we have discussed here. Another kind of important mechanical property of a material is what is called the bulk modulus, and it is represented typically by K, and it is the ratio of the hydrostatic pressure and what is called dilatation. So, dilatation is basically change in volume or the fractional change in volume due to the action of this uniform surrounding pressure on a material. So, if we let us say have a body and we submerge it in a fluid, then typically in a static case uniform hydrostatic pressure will be acting on this material from all directions in a compressive way, and that will tend to or try to compress the material and reduce its volume. So, the pressure acting divided by the fractional change in volume that is produced, that is what this bulk modulus measures. And we have already discussed that the hydrostatic pressure is the average normal stress at a point, and this dilatation or the fractional change in volume, that can be given by just the sum of the all 3 normal strains produced. Okay. So, this ratio is how the bulk modulus is defined. Similarly, we have already discussed Young's modulus. So, if a body is subjected to a uniaxial extension or compression, then the normal stress divided by the corresponding normal stress in that in the direction of extension, that is how the Young's modulus is defined. So, it is a stress by strain, and if let us say if we are deforming the body along the x1 axis, so the corresponding normal stress is sigma 11 and the normal strain or tensile strain is sigma epsilon 11, and their ratio corresponds to the Young's modulus. One more important property is what is called the Poisson's ratio. So, Poisson's ratio, this is represented by nu, and it is defined as the ratio of the lateral or transverse strain produced by the longitudinal or axial strain produced. So, in the general case, if again we consider this as kind of a rod, and if we are pulling it down, then some longitudinal or axial strain will be produced in this direction, direction of the force that is acting, but that can also lead to transverse strain produced in a perpendicular plane. Okay. So, the longitudinal or axial strain will be produced like this, but a corresponding transverse or lateral strain in a perpendicular plane is can also be produced. So, the ratio of this lateral to longitudinal strain, that is what this Poisson's ratio is a measure of. And if we have a longitudinal strain which is positive, so in the case of tensile stress, in that case usually the transverse strain will be negative, and on the other hand, if the longitudinal strain is compressive, then usually the transverse strain will be positive. So, there is a minus sign here, and in most of the cases the sign of the transverse and axial strains are opposite. So, Poisson's ratio many times is positive. So, these are some of the important mechanical properties which are related to the stress and behavior of a material. And for elastically isotropic solids, as we have discussed, there are only two independent stiffness or elastic constants. So, using that condition, it can be shown that these four properties are actually related to each other. So, we will not go into the derivation of those relations, but we will just write down the relationship between these properties that is valid for isotropic elastic solids, where only two independent stiffness constants are present. So, the relationship between the shear modulus and the Young's modulus is through this expression where the Poisson's ratio appears here. The relationship between the bulk modulus and Young's modulus also is through this relation expression, and here the Poisson's ratio again appears here. So, these are some of the important mechanical properties of a material related to the stress and behavior, and we see that for elastic isotropic solids these properties are not independent but are interrelated. And we have also discussed that certain kind of polymers like glassy polymers or some semicrystalline polymers can be thought of as behaving like elastically isotropic. So, for such polymers such expressions are expected to hold. Next, let us talk about the elastic response of these polymeric materials and different types of polymeric materials. So, when we say elastic response or elastic deformation, we will specifically talk about the elastic deformation of these polymeric materials. What we mean is how the stress and strain are related. So, basically a stress strain kind of diagram where the strain measure is a measure of the deformation and stress is measure of the amount of force being subjected or applied on the polymeric material. So, if we consider the case of what is called a single crystal polymer fiber. So, these are polymer fibers where the chains are highly oriented along the fiber axis. Okay. So, again if we consider this as a fiber, the polymer chains are oriented along the fiber axis and the polymer chains are in a crystalline kind of arrangement. So, these are highly crystalline materials where the polymer chains are also highly oriented in one direction. So, because of this strong chain orientation in the axial direction, this material shows a stress strain behavior where a very large amount of stress only produces very small amount of strain. So, the deformations produced for large amounts of forces acting on it will still be very small for such materials. So, these materials typically will show the kind of behavior that is shown here, and at high enough stresses they will exhibit failure, which means that mechanical fracture of this material will take place if the applied stress exceeds a certain point. But we will see that even at the failure point the amount of strain or elongation produced in the material is very small. Okay. So, these are very rigid kind of materials. Next, we can consider the case of glassy polymers. So, we have talked about the glassy polymers when we discussed the glass transition temperature and the amorphous phase of polymers. So, these glassy polymers are amorphous polymer structures which are rigid because the polymer chains are kind of trapped in due to the absence of enough free volume, and the polymer chains are mostly immobile, and this leads to a kind of hard rigid kind of these glassy polymers. So these glassy polymers again show a behavior where the stress, large amounts of stress also do not produce significant amount of strain, but compared to the such single crystal polymer fibers, the corresponding strain produced for a given stress is higher, as we can see here. So if we consider a particular value of stress, the strain produced in this polymer fiber is here, whereas the strain produced in the glassy polymer is here. So we see the larger amount of strain is produced, but still these materials are quite rigid, and if enough stress is applied, ultimately the material will fail or exhibit mechanical fracture. Another class of important polymeric materials are semi-crystalline polymers. So we have discussed the fact that most of the polymers in use can be thought of as semi-crystalline polymers, where which have different degrees of crystallinity, and the polymer itself consists of amorphous phase along with the crystalline phase present together. So for such semi-crystalline polymers, the stress strain behavior actually is a bit different, and initially if we see there is a linear kind of stress strain relationship, but beyond a certain amount of stress, the linear stress strain relationship does not hold, and the elastic, instead of a elastic kind of deformation, we see a inelastic or plastic kind of deformation of the material, and material can undergo long elongations and ultimately might exhibit failure at high enough strains, although the stress itself at which the failure is exhibited need not be very high. Okay. So another important class of polymers is elastomers, which are these rubbery polymers, rubbery cross-linked kind of polymers, and these polymers are characterized by the fact that they show a large amount of reversible extensibility or reversible elongation. So here we see that even for small amount of stresses, in the case of elastomer, very large strains can be produced, and up to very high strain values, actually if the external force is removed, the material will revert back to its original dimension. So the elongation is reversible up to quite a large strain value, but at again high enough stresses and correspondingly large enough strains, the material will exhibit failure. So typically in the stress strain curves that we have shown here, if we measure the slope of these curves at very small values of strain, that slope will correspond to the Young's modulus of these material. So typically for elastomers, the Young's modulus is of the order of 1 to 10 megapascal. So we see that the initial slope is quite small, and the Young's modulus also is quite small for elastomeric materials. For semi-crystalline polymers, the Young's modulus is typically in the range of 100 to 1000 MPa, where MPa is megapascal. So 1000 MPa is essentially 1 gigapascal. Now depending on whether the semi-crystalline, the amount of crystal phase present inside the semi-crystalline polymer, as well as whether the amorphous phase is in a glassy kind of state or not, these are the factors that will dictate exactly what will be the Young's modulus, but typically the range observed is between 100 and 1000 megapascal. For glassy polymer, the Young's modulus is generally high, and it is of the order of 10 to the 3 megapascal, which is equivalent to 1 gigapascal. For polymer fibers, we see that the curve shows a very high slope or very small strains at even very high stresses. So here the Young's modulus is of the order of 10 to the power 2 gigapascals or 10 to the power 5 megapascals. So this is just the order, it's not the exact value. The values of Young's modulus lie in this order of magnitude. So for crystal, for the polymer single crystal fibers, an important thing to note is that although we have written the Young's modulus to be of the order of hundreds of gigapascals, but that is valid only in the longitudinal direction or in the fiber axis direction, because that is the direction in which the chains are oriented or aligned. So that's the direction which shows a high Young's modulus. But these polymer crystals, these fibers are quite anisotropic, and if one measures the transverse elastic modulus or the kind of Young's modulus in the direction perpendicular to the fiber axis, then this transverse modulus values actually are much lower. Transverse modulus values are of the order of 1 gigapascal, whereas the axial or longitudinal modulus is of the order of hundreds of gigapascal. So, due to the strong anisotropy, moduli measured in different directions for polymer fibers are actually different. And finally, we will just discuss the case of semi-crystalline polymers in a bit more detail, because in many cases the polymeric material actually exists as a semi-crystalline polymer where both amorphous and crystalline phases are present. So, if we consider a few examples, so in natural rubber it has been observed that if we have a completely amorphous sample of natural rubber, it shows let us say Young's modulus of the order of 1 megapascal, but if we if crystallization takes place and if the degree of crystallinity increases to let us say 20 or 25% in this natural rubber, then the Young's modulus has been seen to increase by as much as 100 times. Okay. So, this presence of crystalline phase in the polymer actually can lead to significant change in the elastic properties, especially the Young's modulus. And another example would be that of semi-crystalline polymers like polyethylene, where clearly the increase in the degree of crystallinity in the material has been seen to lead to an increase in the Young's modulus of the material. So, what we can infer from these observations is that the elastic properties or elastic behavior of these semi-crystalline polymeric materials actually depends on the strongly depends on the degree of crystallinity in the material as well. Normally, the overall elastic property of the material, let us say the Young's modulus of the material, that will be a reflection of both the elastic modulus of the amorphous phase and the elastic modulus of the crystalline phase in the semi-crystalline polymer. Semi-crystalline polymer can be thought of as behaving as composites, where both the crystalline and the amorphous phases they contribute to the overall elastic modulus of the material, but the way in which the individual elastic moduli of the amorphous and the crystalline phases combine to produce the overall elastic modulus of the material, that usually is something that's not known, and that's not something which can be readily predicted. Okay, so that's a challenge. So the overall modulus is a combined moduli of both the phases, but how these two combine, that is something which is not known for most of the materials. If we talk about few specific cases, okay, because if we have a semi-crystalline polymer, then depending on the size of the crystalline phases present, also the shape of the crystalline phases present and other factors, the individual behavior can vary significantly. So what we'll do is just focus on a couple of specific cases and try to discuss a couple of equations that to some extent can model the Young's modulus behavior of these semi-crystalline polymers. So, if we are talking about a system where we have the crystalline phase exists as single crystal fibers and it is embedded in an amorphous matrix. So, if we are considering a case where the crystalline phase exists as in the fiber kind of morphology and it is assumed to be embedded in the polymer matrix, which is otherwise amorphous. So, for such a case, the Young's modulus of the semi-crystalline polymer EP, that can be related to the Young's modulus of the crystalline part and the Young's modulus of the amorphous matrix, as well as the volume fraction of the crystalline part, by what's called this White model. So, this White model can be used to relate or estimate the Young's modulus of semi-crystalline polymers of this kind of a morphology. Okay. So, as we discussed, the symbols have the corresponding meanings which are written here, and this kind of model can be thought of as representing a case where we have two components in our system. So, our semi-crystalline polymer we consist of as having a crystalline component and an amorphous component. And in this white model, what's assumed is that when it's subjected to a stress, then the strain produced in both the components is equal. So for such a case, an equation like this can be shown to be valid, but it must be mentioned that such equations can only approximately model this kind of semicrystalline polymeric morphology, and exact or very quantitative match may not be obtained. Finally, if we consider a case where the crystalline phase exists as ferrolytic kind of domains. So that's what we discussed mostly in the previous lecture, that in most of the cases when polymer is crystallized from a melt, ferrolytic kind of crystalline domains basically grow and impinge on each other. So if we have a case where the crystalline domains as ferrolytic, and of course we have an amorphous polymer matrix as well, and these crystalline domains are assumed to be embedded in this amorphous phase, so that we have this two-phase semicrystalline polymer, then this Royce kind of model is something that can give some reasonable estimates of the Young's modulus of the semicrystalline polymer. So here we see that the reciprocal of the Young's modulus of the semicrystalline polymer is related to the volume fraction of the crystalline part by the Young's modulus of the crystalline part plus this volume fraction of the amorphous part by Young's modulus of the amorphous matrix. These are some of the models which are not really that accurate, but which allows some kind of rough estimation of the Young's modulus of semicrystalline polymers. So in today's class, what we have done is just gone through some fundamental concepts related to mechanical properties, and then we have briefly discussed the mechanical properties and the elastic deformation behavior of polymeric materials. In the next week, the material that we will cover, in that material we will draw upon some of the concepts that we have discussed today, and we will specifically discuss some interesting mechanical behavior and flow behavior exhibited by a polymeric material. So, we will talk about the viscoelasticity as well as the non-Newtonian flow behavior of polymer solutions and melts, let us say, and we will also discuss the case of rubber elasticity which is exhibited by elastomers. Okay. So, these are some of the things that we will be discussing in the next week, and hopefully the material that we have covered today will come in handy in understanding those concepts. Thank you.